this video, we are going to discuss about Cauchy's second theorem on limit. The theorem is pretty simple. We will know the theorem and then we will know how to apply it in the limits problem. Again, we are not going to prove this theorem right here. We will simply understand the theorem and we will know how to apply it in problems to solve limits at considerable less amount of time. So what does Cauchy's second theorem on limit states? It says that if An is a sequence of real numbers which are all positive, N is a sequence of positive real numbers and N belongs to any natural number. So it states that limit n tends to infinity an whole to the power 1 over n. This limit will be same as the limit an plus 1 over an. If this limit exists, and let us say its value is L, then Cauchy's second theorem on limit states that this limit will also copy this value L. The theorem is as simple as this. Is it clear? So what is the condition? I told you that n is a positive real number sequence. So limit n tends to infinity an whole to the power 1 by n. The value of this limit will be same as the value of limit n tends to infinity an plus 1 over an. If this limit exists and if its value is L, then our given limit will simply copy that value. That's it. That is your Cauchy's second theorem on limit. Okay? So let me take an example. Now see this question. Limit n tends to infinity n to the power n divided by factorial n to the power 1 by n. Now the moment I see that the exponent is 1 by n and n is tending towards infinity, we should always give a thought on Cauchy's second theorem on limits. So first thing that we have to check that our an, which is here is n to the power n by factorial n, whether this is a positive real sequence or not. It is quite obvious that it is a positive real sequence because n belongs to natural number. So all the values that we are going to get from this sequence are positive. So in this case, according to our Cauchy's second theorem, we will find out what is our limit n tends to infinity an plus 1 over an. Because if this limit exists and the value that we are going to have from this will be exactly the same value of our given limit. So this can be written as limit n tends to infinity. What is an plus 1? It will give us n plus 1 to the power n plus 1 divided by n plus 1 factorial whole divided by n to the power n by factorial n, which is actually an plus 1 by an. So which can be simplified further. N plus 1 to the power n plus 1 into factorial n divided by n plus 1 factorial into n to the power n. So after simplification, it will boil down to n plus 1 to the power n plus 1 into factorial n divided by n plus 1 into factorial n into n to the power n. So now we can easily see that this will go off. Okay. Now 1 n plus 1 is in the denominator and n plus 1 whole to the power n plus 1 in the numerator. So we are going to have limit n tends to infinity, n plus 1 to the power n divided by n to the power n. Am I correct? Which can further be simplified to 1 plus 1 by n whole to the power n. Now we know from a standard limit that when limit x tends to 0, 1 plus x to the power 1 over x is basically e. That is, when x is tending towards 0, this part is tending towards 0 and this part is tending towards infinity. That exactly is happening here. When n is tending towards infinity, this part is tending towards 0 and n is tending towards infinity. Therefore, this limit can be written as e only. So, limit n tends to infinity, a n plus 1 over a n, it exists and its value is e. Therefore, our given limit is equals to e. That's it. That is what your Cauchy's second theorem on limit is all about. Is it clear to everyone? Let me take another example. See this question. This limit can be written as limit n tends to infinity, n plus 1, n plus 2, n plus n whole divided by, I am actually taking this n inside the bracket, so it will be n to the power n whole to the power 1 by n. Now n is tending towards infinity and in the power we are having 1 over n. So I have to think about Cauchy's theorem. So in this case our an is this whole thing. Now we will find out what is our an plus 1, which actually gives us, in place of n I am writing n plus 1. So it will be n plus 1 plus 1, n plus 1 plus 2. This thing goes on, n plus 1 plus n plus 1 divided by n plus 1 to the power n plus 1. So actually it comes to n plus 2, n plus 3, this thing goes on. The last term will be 2n plus 2. So the term previous to this will be 2n plus 1. The term previous to this will be 2n and this thing goes on, right? Divided by n plus 1 to the power n plus 1. So this is your an plus 1 and an we have. So let us just find the limit n tends to infinity, an plus 1 over an. And we will check whether this limit exists or not. If it exists, then the value will be same as our given limit. So this can be written as limit n tends to infinity, n plus 2, n plus 3, 2n, 2n plus 1, 2n plus 2, whole divided by n plus 1 to the power n plus 1, whole divided by an. An is n plus 1, n plus 2, last one is 2n divided by n to the power n. So if we further simplify this, you see one thing, these terms will get cancelled, isn't it? X plus 2, x plus 2, x plus 3, then x plus 3 will go off. So 2n as well as this 2n will go off. So we will be left with, in the numerator we will be left with 2n plus 1 into 2n plus 2. N to the power n will go in the numerator divided by n plus 1 to the power n plus 1 and we are left with n plus 1 here. Okay. So that gives us limit n tends to infinity. This is basically coming to, if I take two n common, I mean n common from this one and n common from this one. So n square will be outside. So it will be actually n to the power n plus 2. And this we are going to have 2 plus 1 over n, 2 plus 2 over n, whole divided by, if I take n from, common from this bracket and n common from this bracket, we are again having n to the power n plus 2, 1 plus 1 over n whole to the power n plus 1 into 1 plus 1 over n, correct? Now this two term will go off. As n is tending towards infinity, okay, we can again simplify this little bit. 2 plus 1 over n, 2 plus 2 over n divided by 1 plus 1 over n whole n into 1 plus 1 over n whole square. As your n is tending towards infinity, so this part will tend towards 0, this part will tend towards 0, this part will tend towards 0, right? But in this case, just now I have explained in my previous sum that this is actually tending towards E, right? Therefore, our answer will be in this case 2 into 2 divided by E into 1. So that gives us 4 over E. That's it. Have you understood? Have you understood? You see, two things you have to understand. One is where to apply Cauchy's theorem, and number two, you have to simply evaluate the value limit n tends to infinity an plus 1 over an. That's it. And check whether it exists or not. If it exists, then the given limit in our problem will be exactly the same value that we got from this one. Or if it does not exist, you will say that this Cauchy's second theorem on limits fails. Right? Therefore, in our case, in this case, the value of this limit is 4 over E. And that's your answer. Right? Okay. Let me take another problem. See this question. Here, an is 3 to the power 3n factorial n whole cube divided by 3n factorial, right? So, first of all, it's very clear as n belongs to natural numbers, so it is a positive real sequence. Now, we are having, in our given limit, we are having the exponent as 1 by n, and limit n is tending towards infinity. So, we have to think about Cauchy's second theorem. So, now we will find out what is our an plus 1, which is actually 3 to the power 3 n plus 1, n plus 1 factorial whole cube, whole divided by 3 times n plus 1 whole factorial. So this is your an plus 1. So now we have to find out the limit n tends to infinity an plus 1 over an. So limit n tends to infinity 3 to the power 3n plus 1 into n plus 1 factorial whole cube divided by 3 times n plus 1 whole factorial divided by an. So this thing will go up 3 to the power 3n into factorial n whole cube, right? Now we can easily see here it is 3 to the power 3 times n plus 1 and there is 3 to the power 3n in the denominator. So it will get cancelled and we will be left 3 cube only in the numerator. Now n plus 1 factorial whole cube, which is actually, this can be written as n into n plus 1 into n factorial. This is whole cube because we are having a whole cube over here, right? So this is practically coming to n plus 1 whole cube and factorial n whole cube. So this can be written as n plus 1 whole cube into factorial n whole cube. And we are having 3n factorial, right? Divided by. This thing is basically 3n plus 3 into 3n plus 2 into 3n plus 1 into factorial 3n. 3 to the power 3n, it has already, we have simplified that into factorial n whole cube. So now this and this will go off. This and this will go off. So we will be left with limit n tends to infinity. This is 27 and we are having n plus 1 whole cube divided by 3n plus 3, 3n plus 2, 3n plus 1, right? Now the highest power in n in the numerator is 3, that is n cube we are having in the numerator. That is the highest exponent of n in the numerator. And its coefficient is 1 in that case. And in the denominator also we are having the highest power of n as 3 and the coefficient is 27. Therefore, our answer will be 27 is there into 1. 1 is coming from the coefficient of n cube in the numerator divided by 3, 3 and 3. That is 27, which is actually the coefficient of n cube in the denominator. And we know that limit when x tends to infinity, an x to the power n, an minus 1, x to the power n minus 1 and so on, divided by bn x to the power n, bn minus 1, x to the power n minus 1 and so on. In this case, when x is tending towards infinity, the answer is always the coefficient of highest power of x in the numerator divided by the coefficient of highest power of x in the denominator. So answer is an, bn. In this case also, the same thing I have done. So your answer is 27 over 27. That gives us 1. Hence, the answer for this sum is 1 according to the Cauchy's second theorem. Is it not very simple to use Cauchy's second theorem? Other than taking log on both sides and then manipulating and doing all these things. So whenever you find that limit n is approaching towards infinity and the power and the exponent is 1 over n, always think about Cauchy's second theorem. Right? Let me take another example. See this question? This is a wonderful sum on this topic. Here it has been given that limit n approaches to infinity, we are having n plus 1 factorial whole to the power 1 over n plus 1 minus factorial n to the power 1 over n. Now as a whole, we cannot apply Cauchy's second theorem because here you are not getting a complete sequence whose power is or whose exponent is 1 over n. It has been split into two functions. In two sequences. So in this case, how to handle this sum? But we can observe in this problem that if we manipulate this sum a little bit, that is in the denominator, we have nothing. It means we are having 1. And that 1, if I write in this way, n plus 1 minus n, it's all same. Now this gives a feelings of Stoll-Cesaro theorem. Can you see it? Can you see it? I have already done Stoll-Cesaro theorem in my day 1 class. Those who have not seen it, link has been given in the description. Go and visit that. So it gives a feelings of Stoll-Cesaro theorem like in Stolz-Cesaro theorem, what we have done, when n is tending towards infinity, an plus 1 minus an over bn plus 1 minus bn. If this limit exists, then this limit will be equals to an over bn. Can you remember this? So here we are having some fillings of that, where your an is basically factorial n to the power 1 over n, and your bn is basically n. Isn't it so? So we are finding out that this limit will exist. This limit will exist. If it exists, then this will be, actually this is what? This is actually this. If this limit exists, then this limit should be equals to, according to the SC theorem, this should be equals to an over bn. It means it is coming to limit n tends to infinity, factorial n to the power 1 over n divided by n. Yes or no? Now, at this stage, look at carefully. That is why this sum is so very beautiful. At this stage, it is giving a fillings of Cauchy's second theorem on limits. Isn't it so? Because the power, the exponent is 1 over n and limit n is tending towards infinity. So there is a fillings of Cauchy's second theorem. So this problem is basically a mixture of Stolz-Cesaro theorem as well as Cauchy's second theorem on limits. Well, so in this case what happened? In this case we can write limit n tends to infinity. We can write this thing as factorial n divided by n to the power n whole to the power 1 over n. Okay? Now, let me just take another sequence, let us say Cn, which is our factorial n divided by n to the power n. It is a positive real numbers. This sequence is a positive real sequence. So we can use Cauchy's second theorem. In this case, we have to find out the limit of n tends to infinity, Cn plus 1 over Cn. That is limit n tends to infinity, n plus 1 factorial divided by n plus 1 whole to the power n plus 1 divided by factorial n divided by n to the power n. So that gives us, if we simplify it a little bit, we are going to have something like this, which again turns to, this can be written as n plus 1 into factorial n into n to the power n divided by n plus 1 into n plus 1 whole to the power n into factorial n, correct? Now, this terms will get cancelled. This will go off. So we are actually left with limit n tends to infinity, n to the power n over n plus 1 whole to the power n. So which can also be written as, let me write it here. This can also be written as limit n tends to infinity 1 over 1 plus 1 over n whole to the power n. And as we all know from our standard limit, that this gives us, this actually tends towards e. Therefore, the value of this limit will be 1 over e. Is it clear? So the answer for this problem is 1 over e, and that's your answer. Is this clear to all of you? Have you understood the application of Cauchy's second theorem on limits? So this is how we do problems, and we apply our Cauchy's theorem in limit problems. Whenever we find that limit n is tending towards infinity and the exponent is given to 1 over n, we should always think about Cauchy's second theorem. But this problem was little bit different because here there was a mixture of Stoll-Cesaro theorem as well as your Cauchy's second theorem. Okay? So let me give you one sum for your homework, and you must try this problem and give the answer in the comment section. Until and unless you try, you will forget this theorem. I am repeating that. You will forget this theorem. You cannot carry this theorem till your examination. So the best way to remember it is do this sum and write the answer in the comment box. See you tomorrow. Stay tuned to us and take a very good care of yourself. Thank you so much.